Our project involved both a GUI and a physical build. Our goal was for our GUI to use inputs to calculate the altitude and azimuth of a given star, thus enabling the user to find that star in the sky. Our build was a barn door camera mount powered by a motor that would track the star as it moved through the sky so that the user could get a long exposure picture of it. To use our project, the user would first input their latitude and longitude, the date and time, and the star that they wanted to photograph. The GUI uses this information to give the user the location of the star in the sky. Then the user manually moves their camera so that it is pointed at that star. They then begin the long exposure shot on the camera and press start on the GUI. The motor will move so that the build tracks the star as it moves through the sky and as the camera takes a picture of the star.
The calculations for azimuth and altitude are quite simple once you know where the star is located on the celestial sphere. Every star in the celestial sphere has a data-based right ascension and declination. However, these are dependent on where the vernal equinox or the first point of Aries is at a given time. You can calculate this using the celestial time, which is the time since January 1st, 2000. Once you have this information, user inputted information, and data-based information, you can use the rest of the formulas to calculate the altitude and azimuth. Through internet research and help from Dr. Lent, we decided the best way to move the camera was with a barn door mount. The basic idea is that the all thread will push on the upper board at a certain rate that will change the distance between the two boards by 1 degree every minute, which is the rate the stars change relative to Earth. Using basic trig and the dimensions of the boards, all thread, and gears, we found the motor needed a speed of 10.185 RPMs. Our final design was essentially the same as our plan with a few alterations to how things were connected. Since the GUI calculations are based on user input, we assumed that this was reliable. Also, because the size of the star database, we limited our program to only find 6 stars that had to be near the south bend sky. For the barn door mount to work, the hinge needs to be aligned with the celestial pole, which we assumed the user would do, and to limit the effect of error in the pictures we took, we limited the exposure time to 2 minutes.
When you run the Astrophotography GUI, the first thing you'll have to do is select a star that you want to find. In this case, we'll choose Betelgeuse. I've already entered the year and the day and the time and the longitude and latitude of South Bend. The time is in military time, so at 10 o'clock it is at 22 hours. When you locate the star, to position your camera, it will give you the degrees in a circle from true north, so 360 minus the azimuth, and the altitude. From there, you can verify that you have found your star, and start the picture capture. The motor will run for 6 minutes and 45 seconds up, allowing for 3 long exposure shots, and then 6 minutes and 45 seconds down to reset the motor. From there, you can hit reset, and find another star.
To test our project, we had to run 2 tests, one on the GUI and one on the build. To test our GUI, we compared our results to a site called Stellarium. So based on the data that we inputted to our GUI, we made sure that the resulting altitude and azimuth that the GUI gave was accurate to that on Stellarium. To test our build, we had to make sure that the motor ran for a certain amount of time and it moved the top board up a certain amount of degrees for that time. We calculated that it should move 1 degree every minute, and our tests showed that that was correct. Some problems we faced were mostly with the build, the biggest one being with this gear shown. The gold gear was not tight enough to the motor, so when the motor would run, the gear would not always move with it. So to fix this, we have to create a new bushing to make it tighter. To make sure that our testing worked, however, we decided to put some duct tape around the motor, giving us a constant rate of the speed of the motor.